Lukasz Wyrzykowski. Lukasz, I apologize if I butchered your name. I Googled it.
No, you've done a great job. Yeah.
Awesome.
But
and
I'm not.
You will talk about microlensing linking LSST with Gaia.
Yes.
Lukasz, you can be able to share screen.
No, I'm not able to share my screen yet. Not yet.
Try that again, please.
Yes, now it worked. Thank you. Just a sec.
Lukasz,
Right.
I will give you a vocal warning for your 5 minutes since you're online.
Oh. Right. Can you see my screen?
Yes, we can.
Okay, great. So thank you for this opportunity, and thank you for the invitation to give this talk. I wish I was there in person. Of course, it's much better to talk to people, to real humans, than to their avatars. But I hope we can have at least some discussion afterwards, or maybe on Slack. Okay, so I'm the guy with the difficult surname. I'm a professor at the Warsaw University in Poland. I've been working on microlensing for, well, not as long as Mark, but for something like 20-something years. And in the last decade or so, I've been involved in Gaia, which is a space mission. And I'm trying to use, especially for microlensing by black holes. And I think black holes were not mentioned enough. So let me talk about this in this talk. I just briefly show some faces and names of my collaborators. This is the Warsaw team here. People are also distributed in other places. We collaborate with the whole world, also within the LSST, the TVS and microlensing group. Right. So just if you focus here, you'll actually get the whole idea of my talk. Just a brief comparison between Gaia and Vera Rubin Observatory and LSST in particular. So Gaia is an all-sky survey in space with 1.4 meter mirror. The duration of Gaia and of the observations is about 10 years. It started observing in 2014. It is supposed to last until 2025. The typical cadence is about 30 days. It depends on where you look at the sky, but generally it's monitoring the whole sky, and typically you get some observations every 30 days. And there are all, Gaia is observing the whole sky, but there are also alerts on all sorts of transients, and they come, because it's a space mission, they come within 1 or 2 days delay. So we are automatically, by nature, limited to slower transients. And there is a dedicated Gaia alerts webpage where these alerts are disseminated. So this is kind of an old-fashioned way of disseminating. I'll talk about it more in a second. The photometry, which is used for transients in particular, is, but for the entire Gaia, there is a broad G-band filter, and Gaia is sensitive down to 21st magnitude, more or less. There is also low resolution spectroscopy for every single observation. We call it BP and RP. And there is, on top of that, there is high resolution spectroscopy for the brightest of the stars. But what is most important, I think, in Gaia is the astrometric time series Gaia is collecting for every single source. So essentially, for every object, you get this set of observations. So comparing with LSST, this is a southern hemisphere ground-based survey with much larger mirror, and the duration is about the same as Gaia, and the cadence is also typical. Of course, it depends on the filters. And the alerts are distributed on transients within seconds via brokers. And there is a photometry which goes much deeper. So the main kind of striking difference you see here is that Gaia has these spectra immediately available for every observation. There is this high resolution spectroscopy as well, and astrometry. I'm going to focus mostly on astrometry in a second. So these are the huge advantages of Gaia, which we are trying to exploit. So some more details about Gaia, I will go quickly through it. This is a mission of European Space Agency launched in December 2013. It is located in L2. like James Webb, for example. It's a 10-meter dish, as you see on this photograph. Here, it's a rendering, of course, and it has 0.7 square degree field of view. But as I said, it's a scanning mission, so it's scanning more or less like about 1,000 square degrees every day. And it delivers simultaneously photometry, astrometry, and spectroscopy for about 2 billion stars. And that data is used for distances from the parallax effect, proper motions, chemical composition, spectral types, and many, many more. There is a special consortium consisting of 500 people, mostly in Europe, but there is also a US extension to it called DPAC. And these are the people who are working on the data to make it available to everyone. So there is no use of data internally within Gaia. Myself, me being part of DPAC, I'm not allowed to use data for my own science. I'm only allowed to produce products out of the data so that this is available for everyone. And that's why we have these cyclic data releases, with the first one in 2016, and then the most recent one just a month ago in 2022, data release number 3. We anticipate 2 more data releases because there is still data being collected and still data to be processed. And the Gaia Science Alert is slightly different because this is where Gaia data is being disseminated on essentially daily basis, and these are published. This is Gaia data published every day, or every time there is data on transients seen by Gaia. This is just a picture of the focal plane. You can imagine the scale, and this is one of the largest space cameras ever flown. So now let's get to black holes, and I show this plot here, which I'll then start modifying. So you see masses of black holes and neutron stars as we kind of understand it from gravitational waves, primarily. The blue ones you see, these are gravitational waves black holes. There are gravitational wave neutron stars. And then we also see electromagnetic black holes and electromagnetic neutron stars. So they follow slightly different distributions, which is already puzzling. And it's this picture alone is causing a lot of questions you can ask about dark matter, about mass gap, and so on. I've added a couple of non-interacting systems, some of them discovered very recently, some of them rejected recently as well. But if we plot microlensing sensitivity on top of it, and microlensing is yet another method to probe the black holes and neutron stars population. And myself and Przemek Bruce, we had a couple of papers in last years trying to probe this with using the optical data. But I will add some first cases of candidates for dark lenses found by microlensing. You see the references below. So you see this picture is starting to be filled with new discoveries, independent discoveries through microlensing. How can this be done with Gaia? So let's do some mathematics. So microlensing was introduced already by Somaya and Mark. So just very briefly, so if you have a lensing black hole, there are these 2 images appearing, image plus and image image minus of the source, which is plotted here in the center. We don't see the source, we see the images instead. And then there is this source lens relative motion, which due to space parallax or annual parallax is not a line, it's most likely like a wiggle. So if you're able to measure the size of the Einstein radius and the amount of the microlensing parallax, then you should be able to get a mass of the lens. If you get the mass of the lens, you also need to get the distance, also using the same quantities. Kappa here is a constant. If you know the distance to the source from some other ways, then you can get the distance to the lens. And if you prove this object with that mass and at that distance is dark, and it's not a main sequence star, for example, or a giant, then you have it. Then it's a dark lens. So that's a recipe how to find a black hole using microlensing. So I've color-coded those quantities which you can measure from the data, depending which methodology you want to use, which channel. So from photometry alone, you cannot get everything. It depends on what kind of event you're dealing with. In some cases, you can get the mass of the lens just out of photometry. But in principle, you need to combine photometry, astrometry, and spectroscopy to get all of these ingredients needed for a black hole. And fortunately, Gaia ticks all the boxes. So it provides both everything, photometry, astrometry, and spectroscopy. But what we do, we supplement Gaia data with other surveys, with other observations, like the Ogle, Spitzer data, LCO, and then LSST, of course, that will be the main delivery of LSST. It will be the photometry. For astrometry, you can in principle use VLTI, Gravity, Pioneer, maybe James Webb as well, Roman Space Telescope. It will be delivering astrometry as well. It wasn't mentioned in the past, in previous talks, but it's worth remembering that there is a potential for astrometric microlensing also from Roman telescope. For spectroscopy, you need it for characterizing the sources. So you need fairly large telescopes, and for LSST, you will need even larger telescopes. So the largest available. So this is the recipe for black hole. And there was one already good candidate published just a few weeks ago, first isolated black hole from microlensing, combining photometry and astrometry. So here, an event from 2011 discovered by Ogle has been monitored also with HST, and then the astrometric signal has been detected. So combining these two, the mass was measured, and it's most likely a black hole. Maybe if you look differently at the data, you might interpret the data also as a neutron star. Anyway, this is first showcase showing that with astrometric time series and photometric time series, you can get these dark lenses discovered. So, but this was a very long effort lasting like 10 years and so on, and there was one candidate found. With Gaia, you can actually have an HST-like resolution of the entire sky, and you get astrometric time series as a natural product of Gaia. So from Gaia, you get everything you see on this picture. So the photometric time series, the astrometric time series of the entire sky. So we've been looking for microlensing events in Gaia. In last data release 3, we published a search, archival search for events from 2014, 2017. And you see the locations of those events. There were 363 events found. And every event found by Gaia, seen in Gaia data, has everything we need for them. For data release 3, we were only allowed to publish the photometric time series, but these events are now being studied for the astrometric part. So every single microlensing event found by Gaia is worth investigating whether it was caused by a black hole. So that's why we have the Gaia alert system, which is finding microlensing events. And in the years 2016, 2021, there was about 400 events found. On average, there is 1 to 5 new events found every week. This rate is nothing comparable to Ogle, but you should remember that this is the entire sky. And this is a very conservative search because Gaia Alerts is finding everything, all kinds of transients, not only microlensing. So I mean, supernovae, tidal disruption events, novae, CVs, also disappearing stars, everything what is changing on the sky is alerted through Gaia Alerts. And we only pick microlensing events, and then we do some analysis from the ground. So if you look at this is one of the first events we found in Gaia, and the black points marks the detection of the time of the alert. If you look at this, you will never tell this is microlensing, actually. This looks so weird. So what we did, we used about 50 telescopes, which were operating for a period of about 2 years. And we collected 20,000 follow-up observations to fill the gaps between Gaia observations. As I said, Gaia cadence is very sparse. It's about 30 days. And some of the changes here you see in this light curve, they were happening on a timescale of hours. This was probably the most complex microlensing event ever studied, caused by a binary lens. If you have a binary and also the binary is rotating while lensing, then the model is extremely complex. But here, thanks to Gaia alert, Gaia observations, Gaia detection, and also a set of follow-up telescopes, we were able to produce this very dense light curve, and we were able to measure the mass and essentially all properties of the lensing system. Moreover, for this event, we made a case, and we showed how Gaia astrometry time series looks like. So this was not published in a paper, but this was published as a Gaia image of the week last year. So here you see on top the Gaia photometry plus the follow-up, and then the middle panel shows what we call Gaia astrometry. This is one-dimensional astrometry. I don't want to go into details about this because of the scanning nature of Gaia. Gaia measures the astrometry in only one direction, but thanks to the multiple scans, you're able to retrieve the two-dimensional motion on the sky. So this is the actual Gaia data for that event. And what we showed with Chris Rybicki, my student here, is that if you include microlensing, then you can explain the astrometric signal much better. We essentially use Gaia astrometry to measure the size of the Einstein radius using Gaia astrometry. So this was the first case of Gaia astrometry time series being used for microlensing. And this is a promising case. We showed that for this type of event, this one was extremely complex. So for more simple events, it will be even more simple. So the data is there, and you see the data is started from 2014, and it's going to last. The time series they're going to last until 2025. Here I have an animation. I'll maybe show you very quickly how the system looks and how the photometry behaves. So this is the binary system which is rotating, and you see the set of caustics caused by the binary lens, and then the source, you see it, and the source is actually shown here in blue, but what the red shows is the actual position of the images. And then the fun happens, if the source enters the caustics, then the images start to appear in different locations. And this is what you actually measure. This is what you see on the sky instead of regular parallax motion. That's why this event was so complex, because of the rotation during the microlensing. Okay, so we are studying more events, and there is an example of Gaia 19 BLD here. This event was very bright, and we were able to observe it thanks to Gaia alert. We observed it with Gaia, with Spitzer, when it still functioned. We had a very extensive ground-based follow-up, primarily from LCO, but also we then were able to observe it with VLTI, so get the astrometric measurement as well. But here, thanks to the finite source effect and the dense coverage of the very peak, we were able to derive the dark lens mass of about 1 solar mass at about 5.5 kiloparsecs. But then, as I said, we also used VLTI, so the interferometry in optical and infrared, to observe the images rotating while lensing. And we were also able to measure the size of the Einstein radius for that particular event. Another event, Gaia 18 CBF, was published by my other PhD student, Katarzyna Kruszyńska. This was one of the longest events ever studied. The time scale was about 500 days. So these are the events we are interested in, as Mark mentioned, as they might be caused by massive lenses. So they might have large Einstein radii. For this event, so far what we did, we used the galaxy model to estimate the size of the Einstein radius, and we got the mass of the lens of about 2 solar masses. There is one more event I wanted to show you, which is Gaia 20 FNR. This event is still ongoing. This is a long-term, bright southern event. This is possibly also due to fast rotating binary lens, we think. So this is the data we already have primarily from LCO, but we also have some test data for that event, which makes it extremely interesting to study. But so far, we don't have a good model for this. We think this is due to rotation. This might be a binary black hole or neutron star system somewhere in the galactic plane. It's very far from the bulge. So events like this one is way too bright for LSST, but events like this, the long-lasting ones and crazy ones, are excellent, I think, showcases, and LSST will definitely find many more of those thanks to its sensitivity.
Lukasz,
Okay, I'm almost done. So the very last event I show you was not found by the Gaia alerts. This is one of the events found in DR3. So event from 2015, which was missed by everyone else. So we found it in the archives. So here Gaia published the accumulated astrometric measurements instead of time series. Time series are still being processed, but we've used the measurement of the proper motion and the parallax from Gaia to show that the goodness of fit can be improved much more if we include the microlensing signal in it. And thanks to that, with my student Maja Jabłońska, we estimated the mass. We essentially measured the mass of the dark lens of about 1 solar mass. So this event will also be studied in more detail with proper astrometric time series, but we were able also to use some hints on the astrometric signal, which is already embedded in Gaia data. The last few slides, I'll show you quickly some details about our telescope network. I mentioned it a couple of times. We rely a lot on telescopes providing us with dense photometric measurements. This is something crucial for LSST as well. So we have a network of about 100 small and medium-sized telescopes, and they operate on voluntary or proposal-based time allocation. And we support them, we provide them targets of interest, and then we support them with data analysis and also automated data processing. And for the automated data processing, we've built something what we call Black Hole Tom, of course, to catch your attention. And this is the engine of it. It's a Tom toolkit of open source code developed by clever people at Las Cumbres Observatory. And so here the telescopes can send us their data, raw images, and we process them. We do the photometry, we do the standardization, and then we obtain science-ready data and light curves. This is what we've been using for our follow-up of Gaia microlensing events. But this is, in principle, this can be extended to any type of time domain observations. Any boring variable star can be requested, and our network can observe this. And these are some screenshots of our system. So take a look at this web page, bhtom.space, and feel free to use it, propose targets, or join with your telescope, if you will. So my last slide is actually an invitation to a workshop to come to Sardinia in October. This is a perfect time to go there, where we are going to have our next Gaia Alerts workshop. So we'll be talking about this, and the network will be there, and it would be great to talk more about LSST in that context, so we can exchange information and learn more about what can be done in the next decade. So the registration is open. Please come, and the workshop will be also available in a remote way. So, but of course, it's much better if we could meet in person. So I hope to see you in Sardinia, and I'll stop here and I take questions if there are any. Thank you.
Thank you, Lukasz. Let's thank the speaker. Yeah. Question, Gautam.
Hi, Lucas. Really beautiful talk. With LSST, of course, we're going to be finding microlensing events at much greater distances. And so the relative astrometric value seems to me to be fairly small, because the separations won't be as large if the source is much farther away. Is there any plans for a Gaia successor, something that has even larger aperture and can do precise astrometry at LSST median distances in the galaxy?
Right. Yeah. Good question and good point. That LSST reaching deeper, it will probe different side of the galaxy essentially. So we'll be seeing events from other side of the galaxy. Even though, however, with Gaia we're already probing a large section, at least in microlensing, a large section of the galactic plane with that. But indeed, yes, it would be great to have a successor of Gaia, and there is a plan for something what we call Gaia Near. So near infrared version of the Gaia. The timescale for this is unfortunately something about 2040, 2050. And so you will have to keep LSST running for much longer for these to overlap. But that's the idea, to go to infrared and to reach much deeper to explore the sources at much greater distance.
Let's take one more question, Mark.
Yes, Marc Monnier. Yeah, I was a little bit surprised not to see the MOA telescope in your map of telescopes. They are not partners, or is it something that has been forgotten?
Yes. So the network of telescopes we rely on are actually small telescopes with a very small field of view. So large telescope with like MOA with large field of view, they would not bother observing one source we request. So typically we include in our network telescopes with small field of view, which can observe, single target very quickly. And of course, MOA is delivering survey data, and it's a survey on its own. And the data from MOA, as well as OGLE, as KMTNet, and as ZTF, we of course use it. But as you mentioned yourself as well, these surveys are mostly concentrated on the bulge, while with Gaia we observe the entire galactic plane, both south and north. So we look at places where no one looks, essentially.
Thank you, Lukasz. Let's thank the speaker again.
Thank you.
And I also want to thank